You know how your phone charger takes the power from the wall and turns it into something your battery can actually use? Well, the secret to that magic trick almost always starts with a tiny but massively important component, the diode. Today, we're diving deep into this fundamental one-way gate for electricity.
All right, so here's our game plan. We're going to start with a simple, perfect idea of a diode as this flawless one-way switch. Then we'll get real and look at how they actually behave. After that, we'll check out the clever models engineers use to work with them, see them in action in some super important circuits, and finally, meet a few of their highly specialized relatives.
So to kick things off, let's just strip away all the real-world complexity for a minute. Let's imagine the perfect, ideal diode. What's its one and only job?
Think of it like this. An ideal diode is the ultimate bouncer at the door of a club. It's a perfect one-way street for electricity. It has one incredibly strict rule. Current, you can go forward, no problem. But you are absolutely, positively not allowed to go backward. It's like a perfect valve. Opens one way, slams shut the other.
And this really breaks down that perfect behavior. When current's flowing the right way, it's like a perfect piece of wire, a short circuit, where nothing gets in the way. But try to go the other way, it's like the wire's been cut, a total open circuit that stops everything cold. This extreme on or off behavior, this is what makes the whole idea so powerful.
Of course, we all know the real world is never quite that perfect. So let's step away from that beautiful theory and look at how a real-world diode, what we call a junction diode, actually behaves. This is where things get a lot more interesting.
See, instead of being a simple on-off switch, a real diode's behavior is, well, it's more of a curve. The relationship between the voltage you put across it and the current that flows isn't a straight line. It's exponential, which means a tiny little change in voltage can cause a huge change in current.
A real diode actually lives in one of three different states. Forward bias is basically the on state. Reverse bias is the off state, but it's not perfect. A tiny bit of current, we call it leakage, still sneaks through. And then there's breakdown. If you push enough voltage the wrong way, the dam bursts and current just rushes through. And believe it or not, we'll see later why that can actually be a really useful thing.
So here's the biggest difference from our ideal model. Turning on a real diode isn't free. You have to pay a small price, a little voltage toll. For a standard silicon diode, it's about 0.7 volts. Only after you've paid that cut-in voltage does the gate really swing open and let the current flow.
And just to make things a little more complicated, that 0.7 volt toll isn't set in stone. It actually changes with temperature. As the diode heats up, that voltage drop gets a little smaller. Now, 2 millivolts might not sound like a lot, but for an engineer trying to design a super stable and reliable piece of gear, that's a huge deal you have to account for. Now, as you can imagine, trying to use that complex exponential math for every single circuit calculation would be a total nightmare. It's just not practical. So engineers have come up with some brilliant simplified models to tame that curve and get the job done.
And right here, you see the classic engineering trade-off. You've got the exponential model, which is perfectly accurate, but a real pain to work with. Then, for probably 90% of everyday circuit design, you use the constant voltage drop model. You just say, okay, when it's on, it's a 0.7 volt drop, good enough. And for analyzing tiny little AC signals, you can use the small signal model, which lets you pretend the diode is just a simple resistor. It's all about picking the right tool for the job.
Okay, enough theory. Now for the payoff. Let's see how this humble one-way gate is the hero behind some of the most critical circuits in all of electronics. This is where it gets really cool.
The #1 undisputed heavyweight champion job for a diode is rectification. The power in your wall outlet is AC, alternating current. It's constantly flipping back and forth. But your phone, your laptop, pretty much all of your electronics, they need DC, direct current, that flows in one steady direction. Diodes are the essential first step in making that conversion happen.
Now, the simplest way to do it is with a half-wave rectifier. It just lets the positive half of the wave through and blocks the negative half. Simple, but you're throwing away half your power. A much smarter design is the full-wave bridge rectifier. It uses a clever arrangement of 4 diodes to flip the negative part of the wave over, turning it positive so you can use the whole signal. It's way more efficient. But there's a catch. The output you get from a rectifier isn't a nice, flat, stable DC voltage. It's a series of bumps, like a roller coaster. This choppiness is called ripple, and for sensitive electronics, it's a no-go. So how do we fix that? How do we smooth it out?
The answer is brilliant in its simplicity. You add a filter capacitor. Think of it like a small reservoir for electricity. The capacitor charges up to the very peak of each bump, and then, as the voltage starts to drop, the capacitor releases its stored energy to fill in the valley. This one little component dramatically smooths out that ripple and gets us much closer to a pure DC signal.
And diodes aren't just for power supplies. They're also precision tools for shaping signals. You can build limiting circuits that act like scissors, clipping a signal to make sure it never goes above or below a certain voltage. Or you can build clamping circuits that can grab an entire waveform and shift the whole thing up or down, clamping its lowest or highest point to a specific voltage you choose. Okay, so now that we've got a handle on the good old standard diode, it's time to meet the family. Engineers took that basic one-way gate concept and tweaked it, optimized it, and evolved it into a whole range of fascinating specialized components.
Each of these is just a clever twist on that core idea. A Schottky diode is built for pure speed. A varactor is wild. It acts like a capacitor whose value you can change just by changing the voltage. A photodiode turns light into electricity, and of course, its famous cousin, the LED, does the exact opposite, turning electricity into light. And remember that breakdown region we talked about? A Zener diode is designed specifically to operate there, which makes it an amazing voltage regulator.
So, from a simple one-way gate for current to a whole family of specialized tools, the diode is just absolutely fundamental. If you understand the diode, you're on your way to understanding almost all modern electronics. It just goes to show you the incredible power of a simple one-way rule. And that really makes you wonder, doesn't it? What other one-way functions are just as essential for the technology that runs our entire world?